Okay, guys, good morning and welcome back to Electric Circuits. So, yesterday we have completed our first circuit theorem, that is the linearity and superposition. Okay, and after that, we have seen what source transformation. So, you know when and where to use source transformation and also when not to use source transformation. Okay. So in this session, we'll mainly look at a very important circuit theorem, that is the Thevenin's theorem. Okay. There's also another theorem, which is what the Norton's theorem, which directly follows from Thevenin's theorem. So this is by far among all the circuit theorems, the most important circuit theorem happens to be what the Thevenin's theorem. Okay. So this is what lecture 6. So what is this Thevenin's theorem? Okay. If you have a linear one-port network, so this box, it is what a linear network, and for this box there is only one port. So what is a port? Port is what? A set of terminals through which current can flow into and out of the network. Okay. So these two terminals, let me call them terminal A and terminal B. So these two terminals will form what? A port. Yes. So what is a port? It is a set of two terminals through which current can flow into and out of the network. Okay. And if this is what? A linear network, so this network, it must be a linear network. That means what? This network should be made up of linear elements. Okay. So what elements can be present inside this network? What elements can be present inside this network? You can have some number of independent voltage sources. You can have a few independent current sources. You can also have what? A few resistors. And then you can also have some dependent voltage sources, in fact linear dependent sources. In the same way, you can also have some linear dependent current sources. These are all the elements that are permitted to be present inside this network or the box. Okay. I mean, you might say voltage source and current source are nonlinear, but I always tell you what? Voltage source and current source, these two sources will act as what? Inputs. So they are not really considered to be a part of the actual system. So the actual system will consist of what? Only these elements apart from the independent sources, and apart from the independent sources, all the other elements are what? Linear elements. That is why we can call this overall network as what? A linear network. Okay. And for this linear network, there are only two terminals, and these two terminals will form what? A port. So overall, we have what? A linear one port network. Yes. And the port is what? Set of these two terminals, and this is what? The linear one port network. Okay. Let's say outside of this linear one port network, we have connected some load resistance RL, across which the voltage is what? VL. VL is what? The load voltage. IL is what? The load current. Let's say this is the complete circuit. Okay. So this white color box is what? A linear network. And for this linear network, there is only one port, and that port is what? These two terminals A and B. Okay. And then across this linear one port network, I have connected some load resistance RL. Now, what are we interested in? What are we interested in? We are not interested in voltages and currents inside this white color box. Let us be clear about this. We are not interested in voltage and currents inside the box. Okay. What are we interested in? We are interested in knowing what is the current drawn by the load, that is the load current, and also what is the voltage across the load, that is what the load voltage. In fact, if you know any of these two things, you can easily calculate how much power is being delivered to the load. So we are not interested in voltage and currents inside the box, but rather we are interested in voltage and currents outside this box. Okay. I hope this is clear. Okay. In such a case, if you are interested in voltage and currents outside the box, as is the case here, then you can replace this white color box with a much simplified network. We can replace this white color box with a much simplified network. That is what Thevenin's theorem is telling us. Okay. So according to what Thevenin's theorem, if you have a linear one-port network, but if you are not interested in voltage and currents within the linear one-port network, then you can always replace that linear one-port network with a much simpler network which contains just one voltage source in series with one resistance. Again, this is also connected between what the same two terminals, that is what A and B, and now also outside of this we have the same load resistance across which the load voltage is what VL, through which the load current is what IL. Okay. So this white color box, this new white color box, it is what the Thevenin equivalent of the original white color box which is at the top. So what is inside this white color box? Is it not a real or a practical or a non-ideal voltage source? So because this is what the Thevenin equivalent of this original network, the voltage source is called as what? VTH, or the Thevenin voltage, and the resistance is called as what? The Thevenin resistance, denoted by RTH. Okay. So on the whole, so what is this one? It is the Thevenin equivalent. Okay. Or let me call this as what? Box A, and this as what? Box B. So what is the relation between box A and box B? Box B is the Thevenin equivalent of box A. Okay. Box B is what? The Thevenin equivalent of box A. So look at the Thevenin equivalent, it is a much simpler network, right? Because it contains what? Only one voltage source and also one resistance, that's all. But the original network, it can be a very complicated network or a complex network. But that complex network can be simplified into what? A very simple network, as long as you are not interested in voltage and currents within this network, but rather you are interested in voltage and currents outside this network. In this case, we are interested in maybe the load voltage or the load current, or maybe the power delivered to the load. Now, from the load point of view, both the boxes are identical. From the load point of view, both the boxes are identical. Let's say when you connect the load resistance across the original box or the original network, that is box A, let's say the resulting load voltage is what? Some VL1, and the resulting load current, let it be some IL1. Now when you connect the same load across this box B, and this box B is what? The Thevenin equivalent of box A, Then again across the load you will get some voltage, let it be VL2. You will also get some load current, that is what IL2. Now VL1 and VL2 will be what, equal? Yes or no? So VL1 equal to what, VL2, and also IL1 equal to what, IL2. So in both the cases, for the load voltage and the load current remain the same. So from the load point of view, box A, that is what the original network, is same as what box B, that is the Thevenin equivalent. So from which point of view? So if I make a statement that box A and box B are identical, that is an incomplete statement. These two are not identical by themselves. Okay, box A and box B are identical from the external circuit point of view or the load point of view in this particular case. Okay, so the load cannot really distinguish whether it is connected across what, the original network or the Thevenin equivalent of the original network, because in both the cases the load voltage and load current will remain the same. So what should you say? You should say from the load point of view, yes, box A and box B are identical. Okay, so it is only so from the load or external circuit point of view, box A and box B are identical. I hope you get the point. So it is only from the external circuit point of view or the load point of view that box A and box B are identical. And this is the case most of the time. Most of the time we are only interested in how much power is delivered to the load, or how much current is drawn by the load, or how much voltage appears across the load. We are not really interested in voltage and currents within the actual linear network. Okay, so this is what is Thevenin's theorem telling us. So any complex network, as long as it is what, linear and having only one port, can be replaced with a much simpler network which contains only one voltage source in series with one single resistance, and that voltage source is called as what, VTH, and the resistance is called as what, RTH. Okay, so let us understand what is VTH and also what is RTH. Okay, and before that let me also tell you the definition of the port. So earlier I think I said port is what, a set of two terminals through which current can flow into and out of the network. Okay, but to be precise, any two random terminals will not form a port. Yes, two terminals will form a port. I'll just write a statement. Two terminals of a network will form a port only if the current flowing into the network at one port is equal to the current flowing out of the network at the other port. Okay. So this is the condition for two terminals to form what a port. Two terminals of a network will form a port only if the current flowing into the network at one terminal is equal to the current flowing out of the network at the other, not port, sorry, at one terminal. I'm sorry, this is not port, this is our terminal. So two terminals of a network will form a port only if the current flowing into the network at one terminal is equal to the current flowing out of the network at the other terminal. So this is very plain and simple definition of a port. Okay. So I'll just give you an example. Let's say you have what a network. So this white color box is what a network. And a network can have any number of terminals. Okay. Let's say this terminal A, this terminal B, and this what terminal C. Okay. And let's say the current flowing at terminal A, it is some 10 amps. And let's say the current flowing at terminal C is what, 5 amps. Now the question is, will terminals A and B form a port? Yes. So this terminal A and this terminal B, it is what, a set of two terminals. The question is, will this set of terminals A and B form a port? The answer should be what, either yes or no. Let us just go by the definition of a port. So when will two terminals form a port? If the current flowing into the network at one terminal is equal to what, current flowing out of the network at the other terminal. So if at one terminal 1 ampere is entering, at the other terminal 1 ampere should come out. Only then those two terminals will form what, a port. Now already at terminal A, how much current is flowing? 10 amps is flowing. What direction? Into the network. Now at terminal C, how much current is flowing? 5 amps is flowing out of the network. Now this white color box, is it not a closed volume? Now for any closed volume, KCL has to be satisfied. Let's say this current is what, I. Yes, what is KCL for the closed volume? Now for this white color box, 5 amps is what, leaving, I is also what, leaving, 10 is what, entering. So 10 equal to what, I plus 5. So I equal to what, 5 amps. So look at terminal A. At terminal A, 10 amps is what, flowing into the network. At terminal B, only 5 amps is flowing out of the network. If terminals A and B should form a port, then the same current should enter and leave at the two terminals. Okay, if 10 amps is entering at terminal A, 10 amps also should leave at terminal B. But here only 5 amps is leaving. So the answer is what, no. So A and B do not form a port. So just because you have some two terminals does not always mean those two terminals will form what, a port. Okay. If you take out terminal C, then definitely A and B will form what, a port. Yes or no? If you take out terminal C, then only two terminals will be there. If the network has only two terminals, then definitely those two terminals will form what, a port. But if you have a third terminal, then these two terminals may not form a port. So these two will form a port only if no current flows at terminal C. Then 10 amps will enter at A and the same 10 amps will come out at B. Okay. So there is everything to know about what a port. Let us go back to our actual theorem, that is what, the Thevenin's theorem. So Thevenin's theorem can be applied to what networks? Thevenin's theorem can be applied to linear one-port networks. Okay. So that means what, you should have a box, and for that box there should be only two terminals, and that too you should be interested in voltage and currents outside the box, not within the box. Then only you can replace that box with a much simpler network called as what? The Thevenin equivalent of the network. Okay. So once again, if you have a linear network with only two terminals, then definitely these two terminals will form what? A port. And let's say across these two terminals we connect some load resistance RL. Okay. And if you are not interested in voltage and currents within the box, then you can always replace the box with its Thevenin equivalent, which contains what? VTH in series with RTH. Again, between what? The same two terminals A and B. And then again, outside of this Thevenin equivalent, we still connect what? The same load resistance RL. Let's say the voltage across the load is what? Some VL. Okay. So what is VOC? Okay. Please look at the second circuit. VOC, if you recall, is what? The open circuit voltage. What is this open circuit voltage? It is the load voltage when load becomes open. So it is what? VL when RL tends to what? Infinity. So in this second circuit, when the load becomes open, yes, no current will flow in the circuit, then no drop across RTH, then the entire Thevenin voltage VTH will appear across this open circuit. So what is VOC? It is what? VTH. So what is this Thevenin voltage? It is nothing but the open circuit voltage across the load. Okay. So Thevenin voltage is what? Nothing but the open circuit voltage across the load. So this is what? The original circuit, right? You can take out the load, and in place of the load you can connect what? A voltmeter, and let's say the voltmeter is what? Ideal voltmeter will again behave like what? An open circuit. I hope you are getting the point. This is what? The original circuit, where there is what? A load. You remove the load, in place of load you connect what? A voltmeter. The reading on the voltmeter is nothing but the open circuit voltage, and that open circuit voltage is nothing but the Thevenin voltage. Okay. So Thevenin voltage is what? Nothing but open circuit voltage. Now what is Thevenin resistance? Let's understand what is Thevenin resistance. Okay. Now what will the load do? This is what? The load. Yes or no? This is what? The load. The load is going to look in this direction. Yes, and the load will look in this direction. Yes. I mean, the load can look in any direction. The load can look downwards. The load can look towards the right. The load also can look upwards. But when the load looks towards the right, there is nothing. It won't say anything. So there is no point in looking towards the right. Similarly, the load, if it tries to look downwards, in downwards also there is nothing. I mean, there is no network. So there is no point in looking down. And above the load also there is nothing. So there is no point in looking upwards. But to the left of the load, we have what? The actual linear network. Okay. So when the load looks towards the left, it will look into this network. So when the load looks into the network, the load will see some equivalent resistance. And that equivalent resistance seen by the load when it looks into the network is nothing but the Thevenin resistance. So what is RTH? So the load, so when I draw an arrow mark like this, okay. So when I draw an arrow mark like this, that means what? Somebody is looking in this direction. But here, who is looking in this direction? The load is looking in this direction. And when I draw this kind of arrow mark, and below the arrow mark, if I write R equivalent, it means the equivalent resistance seen in this direction. Yes. So when the load looks in this direction, the load will see some or find some equivalent resistance. That equivalent resistance is nothing but the Thevenin resistance. That's all. So I hope now you have understood what is Thevenin voltage and what is Thevenin resistance. Okay. So Thevenin voltage is same as what? The open circuit voltage, and Thevenin resistance is same as what? The equivalent resistance seen by the load. Okay, again I'll just write a couple of lines. Thevenin voltage is nothing but the open circuit voltage across the load, and then Thevenin resistance is nothing but the equivalent seen by the load looking into the network. So these are Thevenin voltage and Thevenin resistance. Okay. So once again, let's say this is what the original linear network, and let's say it has got only one port, and across this linear one port network, let's say we connect some load resistance, and we are only interested in the voltage or the current or the power with respect to the load. We are not interested in voltage and currents within this box. In such a case, I told you what, you can replace this box with its Thevenin equivalent, which contains a single voltage source VTH in series with a single resistance called as what, RTH. Once again, across the Thevenin equivalent also we connect what, the same load. Okay, let this be A, let this be B. Okay, so what is this yellow color box? This yellow color box, it is what, the Thevenin equivalent of the original network. Okay, now what is inside the yellow color box? A voltage source in series with resistance. Again, going back to source transformation, if you have a voltage source in series with resistance, and if you are interested in voltage and currents outside this combination, then you can always transform this into what? A current source in parallel with the same resistance. So what is the value of the current source? The value of the voltage source divided by the resistance in series, that is what, VTH by RTH, and then the same resistance will now appear in parallel. Okay, again this is what A, this is what B. Even this combination is connected between what, the same 2 points A and B, and outside of this we still connect the same load resistance, that is what, RL. Okay, so look at this new box. Look at this new box. So what is this green color box? So even this green color box is what, some kind of equivalent of the original. Okay, so this is what, the original network. So first we have replaced the original network with its Thevenin equivalent, and then for the Thevenin equivalent I have done what, source transformation. Okay, so first I have used what, Thevenin's theorem, and then to go from yellow color box to green color box, I have resorted what, source transformation. Okay, now this green color box is also what, some type of equivalent of the original network, and this green color box contains what, a current source in parallel with a resistance. Yellow color box is what, voltage source in series with some resistance. This is what, current source in parallel with resistance. This is called as what? The Norton equivalent of the original network. So the original network can be replaced with two types of equivalent or simplified equivalent networks. One is called the Thevenin equivalent. The other one is what? The Norton equivalent. Okay. Now let us focus on the Norton equivalent. Current through RL, would it not be IL? Yes, current through RL is what? IL. Now we have this thing called ISC, right? Just like VOC is what? Open circuit voltage. Yes or no? Just like VOC is what? Open circuit voltage across the load. ISC is what? The short circuit current through the load. So ISC, it is what? The load current. That is IL when the load becomes what? 0. Or when the load becomes what? A short circuit. So when RL becomes 0, it becomes what? A short circuit. Whatever current will flow in the short circuit, that is what? The short circuit current through the load. In this case, when the load becomes short circuit, this entire current will it not flow only in the short circuit, because drop across short circuit is what? 0. Then drop across this RTH also will become what? 0. 0 drop means what? 0 current through the internal resistance, and the entire source current will only flow through the load. So what is ISC? It is equal to what? The source current, that is VTH by RTH. Okay. So this, because this is what? The Norton equivalent, the current source is denoted by IN, that is what? The Norton current, and the resistance is denoted by RN, that is the Norton resistance. Just like RTH is what? The Thevenin resistance, RN is what? The Norton resistance. Just like VTH is what? The Thevenin voltage, IN is what? The Norton current. Okay. And what is the value of the Norton current? It is VTH by RTH. Okay. That's all. And of course, RN equal to what? RTH. Yes or no? The Norton resistance is same as what? The Thevenin resistance. Norton resistance is same as what? The Thevenin resistance. Okay. So we have three quantities. Number one is what? VTH. That is what? The Thevenin voltage, which is same as what? The open circuit voltage across the load, which is same as what? The load voltage when the load resistance tends to what? Infinity. And then we have what? The Thevenin resistance, which is same as what? The Norton resistance, and it is equal to what? R equivalent, that is what? The equivalent resistance seen by the load. The third quantity is what? The Norton current, which is same as what? The short circuit current. Yes, and the Norton current is same as what? The short circuit current. So IN equal to what? ISC. And short circuit current means what? It is the load current when the load becomes a short circuit. IL when RL becomes what? Or RL tends to what? 0. Okay. And what is the relation between VOC and ISC? So if you look at here, VTH by RTH is what? IN. So RTH equal to what? VTH by IN. So RTH is simply what? The ratio of the Thevenin voltage to the Norton current. Thevenin voltage same as what? Open circuit voltage. Norton current is same as what? The short circuit current. That is VOC by ISC. Yes. So the the Thevenin resistance is same as what? The Norton resistance, and both are equal to what? Ratio of VTH to IN, that is ratio of VOC to ISC. Okay. I hope it is clear up to this point. So if you are given some linear network, so this box, it is what? A linear network, and it has only one port. Let the two terminals be what? Some A and B. and across this linear one port network some load resistance is connected. Okay, and then you are in the lab, and then you are what in the lab, and you would like to find the Thevenin equivalent of this linear one port network. So you can conduct two experiments, because finding Thevenin equivalent means what? Finding VTH and RTH. VTH means what? VOC. RTH means what? VOC by ISC. So you can perform two separate experiments. In the first experiment, we'll replace RL with what? A voltmeter. We'll replace RL with a voltmeter. So look at this. So in place of RL, I will connect what? A voltmeter. And let's say this voltmeter is what? Ideal. Ideal voltmeter won't draw any current. So in other words, the load has become what? An open circuit. Yes. Now this voltmeter will try to measure the voltage across this open circuit. So reading on the voltmeter will be what? VOC. Yes. So reading on voltmeter is nothing but VOC, and VOC is nothing but the Thevenin voltage. Okay. So what is the objective here? Find Thevenin equivalent of the network, let's say experimentally. Find Thevenin equivalent of the network experimentally. So for that we have conducted one experiment. Let us conduct another experiment. In the other experiment, what we'll do is we'll replace RL with an ammeter. Replace RL with ammeter. Replace RL with ammeter. Look at this. So once again we have what? The original circuit or the network, and this time I'm going to replace RL with an ammeter. Again, let's say the ammeter is what? Ideal. Ideal ammeter will behave like what? Short circuit. Ideal voltmeter will behave like what? An open circuit. Okay. So when this ideal ammeter acts like a short circuit, it is as if load is what? Replaced with a short circuit. So some current will flow through this short circuit or the ammeter, and that current is nothing but ISC. So the point is what? Reading on ammeter is nothing but ISC, and ISC is nothing but the Norton equivalent. What is our goal? It is to find the Thevenin equivalent. Yes, finding Thevenin equivalent means what? Finding the values of VTH and RTH. Already VTH is what? Reading on voltmeter. Now finally RTH, you know, is what? VOC by ISC. That is reading on voltmeter by reading on ammeter is nothing but the Thevenin resistance. That's all right. Reading on voltmeter is what? The Thevenin voltage, and the ratio of VOC to ISC is nothing but the Thevenin resistance. In this way, yes, without doing any calculation, just by conducting two simple experiments on the given network, we can easily find the Thevenin equivalent. If you know Thevenin equivalent, then by doing source transformation, we immediately get the Norton equivalent as well. Okay. So is it clear? Yes. So once again I reiterate, when can we use this Thevenin's theorem? If you have a linear one port network. Yes. Just a second. Sorry. So when can we use this Thevenin equivalent? We can use this Thevenin's theorem when you have a linear network that has only one port, and if you are not interested in voltage and currents outside this, inside this linear network, yes. So generally outside this linear network we connect what a load resistance, but it is not compulsory that you should always connect what a load. You can connect anything outside this linear network, yes. But for Thevenin's theorem to be applicable, this box has to be what? Linear. Outside the box you can have linear or non-linear elements or networks, okay. In fact, outside this box, let's say we have another network itself, okay. So this is what, so let's say this is what, like network A, and this is what, network B, yes. And we are interested in voltage and currents in network B. We are interested in voltage and currents inside network B. We are interested in voltage and currents inside what? Network B and not network A. Yes. So because we are not interested in voltage and currents inside this network A, and because network A is what? Linear, we can replace this network A with its Thevenin equivalent, okay. So network A can be replaced with its Thevenin equivalent, which is VTH in series with RTH. But outside of this, we still have what? The same network B, okay. So this is still the same network B, yes. So when you do this, the voltage and currents inside network B will not change, okay. I hope you have understood, okay. And here, to be able to replace network A with its Thevenin equivalent, there is no condition on the nature of network B. Network B can be what? Linear or non-linear, but still you can replace network A with its Thevenin equivalent as long as network A is what? Linear, and you are not interested in voltage and currents within network A, okay. So here there is no condition on the nature of network B. In other words, network B can be linear or non-linear. Network B can have any nature. Basically, that is the point, okay. So I need to make one more very important point. Listen to this carefully. So this is what? Linear network, and this has got two terminals which will obviously form what? A port. So on the whole we have what? A linear one port network, yes. And let's say across this linear one port network, originally we have some load resistance RL, okay. or not load resistance. Let's say we have a voltage source Vt, T for test. Okay, so Vt is what? A test voltage source, and let the current flowing out of the plus terminal of this test voltage source be It, again T for test. Generally we connect what? Load, but here I have not connected what? Load. Instead I have connected what? A voltage source Vt. Yes, and we are interested in finding the relation between Vt and It. So we would like to find what? Relation between Vt and It. We would like to find the relation between Vt and It. That means what? Clearly we are not interested in voltage and currents inside this box, but rather we are interested in voltage and current outside the box. Whenever that is the case, can't you replace this box with its Thevenin equivalent? It won't affect voltage and currents outside the box. It also won't affect the relation between Vt and It. So connecting a voltage source Vt across the original linear network is same as what? Connecting the same voltage source Vt across the Thevenin equivalent of the original network. So what does a Thevenin equivalent have? It contains Vth in series with Rth. Yes, and then again outside this we have what? The same test voltage source Vt, and this current flowing out of the plus term is what? The same It and so on. Okay. Now what is this current? It is what? It. So what is the drop across Rth? It is what? It times Rth. Now can't we write KVL around this loop? So if you write KVL around this loop starting from this point, you will get minus Vth minus It times Rth plus Vt equal to what? 0, or Vt equal to what? Rth times It plus Vth. This is an extremely important result. Vt equal to what? Rth times It plus Vth. That is the relation between the test voltage and the test current. That is what? Vt and It. Anyway, I'll just write it separately again. So what is the relation between Vt and It? It is the following. So Vt equal to what? Rth times It plus Vth. That is the relation between Vt and It. So in general, the relation between Vt and It. So in general, the relation between Vt and It will be of the form Vt equal to what? Ait plus B. In general, the relation between Vt and It will be of the form Vt equal to what? Ait plus B, where A is what? Compare this with this equation. Yes or no? If you compare these two, then A is nothing but Rth. Yes or no? A is nothing but Rth and B is nothing but the Thevenin voltage, that is what? Vth. Understood? Yes. That is the relation between Vt and It. Vt equal to what? Ait plus B, where A is what? Rth, the Thevenin resistance, and B is what? The Thevenin voltage, that is what? Vth. Okay. Okay. Once again, let's say we have what? A linear network. In general, linear network will contain what? Independent voltage sources, independent current sources, resistors, linear dependent voltage and linear dependent current sources. Okay, and let's say across this linear one port network. So this is what a linear one port network. I connect a test voltage source Vt, let the current flowing out to the plus terminal be some It. Then what is the relation between Vt and It? Vt equal to what? AIT plus B, or Vt can be written as what? A is what? RTh, right? Vt equal to what? RTh times It plus B is nothing but Vth. So there is the relation between Vt and It. RTh times It plus Vth. Now I take the same network, but I'll make the what? The independent sources 0 in the same network. Now I'll make the independent sources 0. Okay, just copy it. Same network. If I make the independent sources 0, that means what? Inside the box, whatever independent voltage sources we have, we make them 0 or short circuit. And inside the box, whatever current sources we have, we make them 0 or open circuit. Okay. Now there are no independent sources within the network. Now what is the relation between Vt and It? When the independent sources are made 0, yes, see, in a circuit, currents will flow only because of independent sources. If there are no independent sources, then every voltage and every current will be 0. Yes. If there are no independent sources in the network, then no currents and voltages will exist in the network. In other words, every voltage and every current will be 0. And this means VOC, yes, VOC and ISC are also going to be 0. Yes or no? When I say every voltage and every current is 0, that includes every voltage and every current. Even open circuit voltage and short circuit current will be 0 when there are no independent sources in the network. Okay. So if there are no independent sources in the network, then directly we can say VOC and ISC are 0. If VOC and ISC are 0, so here when you make the independent sources 0, what is VOC? 0. So what is VTH? It is what? 0. Then what is the relation between Vt and It? When Vth becomes 0, it is this term that becomes what? 0. When this term becomes 0, then the relation becomes what? Vt equal to what? Rth times It. So what is Rth? It is Vt by It. So throughout analog circuits, whenever we wanted to find, the equivalent resistance, be it the input resistance or the output resistance, always we use this Vt by It method, right? So how do we find the equivalent resistance? You connect that voltage source Vt, let the current flowing out of the plus terminal be some It, and then you make all the other independent sources 0. Then I always say the equivalent resistance is what? The ratio of Vt to It. But this is how that method comes about. Okay. So here deliberately we have made all the independent sources inside the box 0. So that the Thevenin voltage will become what? 0. Then the relation between Vt and It will become what? Like this. Vt equal to what? Rth times It. So from there Rth is what? Vt by It. So if I give you a network and if I ask you to find only the Thevenin resistance, then you can simply connect a voltage source Vt outside the network, and then you make all the independent sources within the network 0, and then you find the ratio of Vt to It. That is nothing but the Thevenin resistance. So this is like the universal method of finding Thevenin resistance of any network. Okay. So this will work for any network without any exception. Okay. That's all. This is all the background that you require of this Thevenin's theorem or the Thevenin equivalent or even the Norton equivalent. Okay, so now we'll start looking at actual circuits, and for every network we'll try to find the Thevenin equivalent. That is the main objective. Okay. So let's say we have what? A linear network. So this is what? A linear network, and this linear network has got only two terminals. So definitely these two terminals will form what? A port. And across these two terminals I have connected what? A voltage source Vt, and the current flowing out of the plus terminal is what? It. Yes. And then four different Vt and It relations are given. Okay. So this is what A, this is what B, this is what C, this is what D. And for each case you have to find what? The Thevenin equivalent. So find the Thevenin equivalent of this white color box, that is a linear network, for each case. For every case, what is given? The relation between Vt and It is given. Now you have to compare it with the standard form. What is that standard relation between Vt and It? Vt equal to what? Some Ait plus B. Okay. So if you compare this with Vt equal to what? Ait plus B. A is what? 2.5. B is what? 3. That means A is what? Rth. B is what? Vth. So for the first case, the Thevenin voltage, you should say it is what? 3 volts. And the Thevenin resistance, it is what? 2.5 ohms. Okay. And then if you look at the second case, B case, It is what? 3 Vt plus 4. It is not really in the standard form. You have to manipulate it and express it in the standard form. Okay. Look at this. So the B case can be written as what? Vt equal to what? 1 by 3 It plus minus 4. Yes or no? 1 by 3 It plus minus 4. I mean minus 4 or minus 4 by 3. So Vt equal to what? 1 by 3 It and then plus minus 4 by 3. Now this is what in the standard form, which is Vt equal to what? Ait plus B. Now by comparison, VTH is what? B, which is minus 4 by 3 volts, and RTH is what? A, which is 1 by 3 ohms. It is what? 1 by 3 ohms. Okay. Okay. Now look at the C case. C case VT equal to what? Minus 5. So C case VT equal to what? Minus 5, which can be written as what? VT equal to what? 0 IT plus minus 5. Yes or no? 0 IT plus minus 5. Now you compare it with the standard form A IT plus B. So what is VTH? It is minus 5 volts. And what is RTH? It is what? 0. Okay. And finally D case, VT equal to what? 105 IT plus 0. You can compare it with the standard form AIT plus B. So what is B? 0. So what is Thevenin voltage? It is what? 0. What is A? 105. So what is the Thevenin resistance? It is 105 ohms. Okay, so these are the values of VTH and RTH. Okay, in each case. So all you have to do is what? Every given relation should be compared with the standard form. That is VT equal to what? AIT plus B, where A is what? RTH and B is what? VTH. Okay. Okay, look at this question. You have to find what? The Thevenin equivalent across RL. Yes, using what? Source transformation. Using source transformation. So when I say find Thevenin equivalent across RL, that means what? With respect to RL, the remaining network, with respect to RL, the remaining network should be replaced with a single voltage source in series with a single resistance, that is VTH in series with RTH. And what is this? Equivalent, Thevenin equivalent. And you have to find the Thevenin equivalent using what? Source transformation. You can easily do it. Okay. But I hope you have understood the equation. Okay. So with respect to RL, this box should be replaced with its Thevenin equivalent. Yes. So what is source transformation? First you have this 12 volt source in series with 3 ohms, which will become what? 12 by 3, 4 amps in parallel with 3 ohms. Yes or no? First it will become like this, 4 amps in parallel with 3 ohms. But then you have what? The original 6 ohm resistor. So 3 parallel 6 is what? I think 6 into 3, 2. So this is same as what? Like 4 amps in parallel with 2 ohms, which can again be transformed into what? A voltage source of value 4 times 2, that is what? 8 volts in series with 2 ohms. And then we have this 7 ohm resistor. Yes. And then we have this, load resistance. That's all. Now 2 ohm and 7 ohm both are in series. They become what? A single 9 ohm resistor. So what is the final Thevenin equivalent or the final answer? 8 volts in series with 9 ohms. And then we have this RL. Okay. So this is what the Thevenin equivalent. So what is the Thevenin voltage? It is 8 volts. And what is the Thevenin resistance? It is what? 9 ohms. Okay, so VTH is what? 8 volts. And RTH is what? 9 ohms. Okay. Okay, look at the next question. So you have to find what the Thevenin equivalent across A and B. So A is here, B is here. By finding what VOC and ISC, that means what separately you have to find the open circuit voltage and also the short circuit current, and from the values of VOC and ISC you have to find what the Thevenin equivalent. Again I repeat, finding Thevenin equivalent means what? Finding the values of VTH and RTH. Okay. So here generally we connect what? A load, but that load is not connected. So because load is not present, you can connect the load across A and B and let the load voltage be some VL, let the load current be some IL. Okay, and then you have to find what? VOC and ISC. So first we will find what? VOC. So number one is what? Finding VOC. So what is VOC? It is the open circuit voltage across the load. Four volts. Then we have 2K. Then we have what? Vx by 4000. And then we have this 3K. And then we have the two terminals A and B, across which the voltage drop is what? Vx. And because we are finding what? The open circuit voltage across the load has to be removed. So when you remove the load, you get this open circuit. Okay. Anyway, I'll just copy this. So now we have to find what? The open circuit voltage. Yes. So when the load is removed, you get this open circuit, and then we have this VOC. So it's all about finding what? The value of VOC. So what is Vx? Is it not same as VOC? And how much current will flow in this branch? Because of this open circuit, the current is what? 0. So what is this current? It is Vx by 4000. So what is this current? Because no current flows through what? 3K. This entire current will flow through what? 2K. So what is the current through 2K? It is Vx by 4000, which is what? VOC by 4K. Yes or no? VOC by 4K. Now VOC by 4K flowing through 2K. 4000 is what? 4K. So what is the drop across 2K? VOC by 4K into 2K. It is what? VOC by 2. Okay. What is the drop across 3K? It is what? 0. Now let us apply KVL around this outer loop starting from this point. So when you write KVL, what do you get? Minus 4 minus VOC by 2 plus 0 plus VOC by 2 plus VOC equal to what? 0. So this is how we write KVL around this outer loop. VOC minus VOC by 2 is what? VOC by 2 equal to 4. So what is VOC? It is what? 8 volts. VOC is what? 8 volts. In the same way, let us find ISC. Let us find ISC. ISC means what? The short circuit current through the load. ISC means what? The short circuit current through the load. So when the load, so this time the load should be replaced with what? A short circuit. Yes. So look at this. The load has been replaced with a short circuit, and whatever current flows in the short circuit, that is what ISC. Now what is the value of Vx? Now Vx is what? The drop between A and B. And now because load is what? Replaced with short circuit, A and B are shorted together. So the value of Vx is what? 0. Then the value of Vx by 4000 is also what? 0. So what is this current? ISC. What is this current? Also ISC. Now this ISC, it is very much like the loop current. Okay. So ISC will be what? 4 volts divided by the net resistance in the loop, that is 2K plus 3K. Yes, 4 volts by 5K. 4 by 5 is what? 0.8 milliamps. That is what the value of ISC. But the question is what? To find Thevenin equivalent, right? Finding Thevenin equivalent means what? Ultimately, you should write the values of VTH and RTH. So VTH is same as what? VOC equal to what? 8 volts. And then RTH is what? VOC by ISC. Yes, VOC by ISC. 8 volts by 0.8 milliamps is what? 10 kilo ohms. So VTH, the Thevenin voltage is what? 8 volts. And the Thevenin resistance is what? 10 kilo ohms. So you can replace this entire network with a single voltage source in series with a single resistance. Okay, like this. 8 volts in series with 10 kilo ohms connected between what? The same 2 points A and B. So this pink color network is what? The Thevenin equivalent of the original network. Okay. Okay, look at the next question. There is some circuit or some network, and you have to find what? The Thevenin equivalent across A and B. You have to find what? The Thevenin equivalent across A and B. Okay. That means what? This network should be replaced with the Thevenin equivalent VTH in series with RTH. Are there any independent sources inside the network? Inside the network, we have what? 2 resistors, 3 ohm and 2 ohm, and 1 dependent source. No independent sources. No independent sources, that itself means what? The Thevenin voltage and the Norton current both will be 0. Yes or no? No. Independent sources in the network, it means what? VOC and VTH both will be 0. Now what is the other thing we need to find? RTH. RTH is what? VOC by ISC. So here not only VOC will be 0, even ISC will be what? 0. So if at all you think you can find RTH by using what? The fact that RTH is what? VOC by ISC, you cannot do it that way, because VOC is what? 0, ISC is also 0. 0 by 0 is what? Indeterminate. You cannot really find RTH using that method. Okay. And also, because there is this dependent source, you cannot simply find the equivalent resistance by using what? Series parallel combination. For example, let's imagine this dependent voltage source is not there. It is what? Short circuit. Then this 3 ohm and 2 ohm both will be in parallel. Then you can say the equivalent resistance between A and B is what? 3 parallel 2, which is 3 into 2 by 3 plus 2, 6 by 5 or 1.2 ohms. That will be what? The Thevenin resistance. But here we have what? The dependent source. We cannot find the Thevenin resistance by using simple series parallel combination of resistors. Okay. So the only way to find RTH is by using that VT-IT method. Okay. So across the two terminals A and B, we have to connect what? A voltage source VT and let this current be IT. Now, because there are no independent sources in the network, VT by IT will be the Thevenin resistance. Okay. So here, what is the value of I? I and IT both are flowing in opposite directions. So I is what? Like minus IT. What is the drop across 2 ohms? It is what? VT. So what is the current through 2 ohms? It is what? VT by 2. Okay. Again, what is this current? It is what? IT. Yes. Now at this point, IT is what? Like entering, and VT by 2 is what? Leaving. Yes. So if I ask you, what is this current? You should say it is what? VT by 2 minus IT. So there will be some drop across 3 ohms. Yes. And then if you want, you can apply KVL around this loop. Let us apply KVL around this loop. Okay. So what is KVL going to be around this loop? So it will be what? Minus 1.5 I plus 3 times the current through 3 ohms, which is VT by 2 minus IT, and then plus VT equal to what? 0. But remember, I is what? Minus IT. So in place of I, if you write minus IT, it will become what? Plus 1.5 IT plus 1.5 VT minus 3 IT plus VT equal to what? 0. So 1.5 VT plus VT is what? 2.5 VT equal to what? 3 minus 1.5, which is 1.5 IT. Now what is the Thevenin resistance for us? It is ratio of VT to IT. VT by IT will be what? 1.5 by 2.5, which is 3 by 5 or 0.6 ohms. That's all. So this yellow color box can be replaced with a single resistance of value 0.6 ohms, because the Thevenin voltage is what? 0. So if you are standing here and if you look into this yellow color network, from this person's point of view, this entire yellow color box will appear like what? A single resistance of value 0.6 ohms. So he will think this network is what? A simple resistance of value 0.6 ohms. Understood, right? Yes. So what are the final answers? VTH is 0 and RTH is what? 0.6 ohms. These are the final values of VTH and RTH. Please read the next question. So in this circuit, the question is what? To find the Thevenin equivalent seen by means what? Across the 100 volt source. Where is the 100 volt source in this network? This is what? The 100 volt source. So with respect to 100 volt source, you have to replace the remaining network. With respect to the 100 volt source, you should replace what? The remaining network with a single voltage source in series with a single resistance. That is the meaning of finding Thevenin equivalent seen by 100 volt source. That means what? the entire remaining network. So look at this green color network. This entire green color network should be replaced with a single voltage source in series with a single resistance. Okay, you can find this Thevenin equivalent in multiple ways. So because you are asked to find Thevenin equivalent seen by 100 volt source, you can consider the 100 volt source as the load, and the remaining network should be replaced with its Thevenin equivalent. Okay, one thing we can do is what? Repeated source transformation. Okay, look at this. 8 amperes in parallel with 50 ohms can be transformed into what? 8 into 50, 400 volts in series with 50 ohms. Yes or no? 400 volts in series with 50 ohms, and then this 30 ohm will appear in series. Yes. And then again we can do what? Source transformation. 50 and 30 both are in series. Yes. So 400 volts in series with 80 ohms can be transformed into what? A single current source of value 5 amps in parallel with 80 ohms. And then you go to the other side. On the other side we have what? 60 volts first in series with 30 ohms, which can be transformed into what? 260 by 30 is what? 2 amps in parallel with 30. Okay. So we can do source transformation like this. Okay. 2 amps in parallel with 30, and then in parallel with this 60. What is 60 parallel 30? It is 20. So this becomes what? A single 20 ohm resistor, and then this is what? The 2 ampere current source. Okay. Now look at this. So this is what? The original 100 volt source, and to the right of the 100 volt source, again we have done some source transformation to get a network like this. Sorry, this is what? 20 ohms in parallel with 2 amps. Okay. Now the two current sources, okay, 2 amps and 5 amps, both are in parallel. They can be combined into what? A single 7 ampere current source. Okay. And also 80 ohm and 20 ohm are connected in parallel, which can be combined into what? 80 parallel 20. 8 into 2, I think 16 ohms. Correct, right? 80 parallel 20 is what? 16 ohms. So 7 amps in parallel with 16 ohms, which can again be transformed into what? A volt, because we are required to find what? The Thevenin equivalent. So what is the 7 ampere in parallel with 16 ohms? It is the Norton equivalent. Yes or no? Single current source in parallel with single current source, single resistance, it is what? The Norton equivalent. Using source transformation, we can get the Thevenin equivalent. I think 16 into 7 is what? Some 112 volts. In parallel with the same 16 ohm resistor, and then of course we have what? The original 100 volt source. That's all. So finally, across the 100 volt source, we have a single voltage source in series with a single resistance. So the value of VTH is what? 112 volts, and the value of RTH is what? 16 ohms. These are the values of VTH and RTH. So by doing repeated source transformation, we are able to find the Thevenin equivalent seen by the 100 volt source. Okay. Another way could have been what? You could have replaced 100 volt source with an open circuit, and then you can find VOC. and then you could have replaced a 100 volt source with a short circuit, and then you could have found the short circuit current, that is what ISC. And from VOC and ISA also we can get VTH and RTH. Or else if you want to find only RTH, RTH means what? Equivalent resistance seen by the 100 volt source. Yes, if you want to find the equivalent resistance seen by the 100 volt source, make all the other independent sources 0. That means what? This current source and this voltage source, you make them 0. And then you find the equivalent resistance across the 100 volt source. Okay. When you make the current source 0, it becomes what? 0 or open. Then 30 and 50 will be in series. Okay. Which is what? 80. And when you make the 60 volt source 0, it becomes short. Then 30 and 60 will be in parallel, which is 20. And then this 20 and 80 will be in parallel. So the net resistance will be what? The same 16 ohm resistor. That is also one way to do it. Okay. Okay, look at the next circuit. So in this circuit, we have to find what? The Thevenin equivalent across A and B. That means what? This network, this yellow color box should be replaced with its Thevenin equivalent. Again, here there is no load. If at all you want to connect the load, you can connect the load like this. Okay. See, finding Thevenin equivalent means what? Finding the values of VTH and RTH. Okay. Again, if you notice, inside the yellow color box there are no independent sources. So directly we can say that the Thevenin voltage, which is same as what? The open circuit voltage, it is what? 0. Yes. So the only thing we need to find is what? RTH. Again, because of this dependent source, you cannot find RE equivalent directly by using series parallel combination of resistors. The only way to find RTH is by using that VT-IT method. Okay. So what is that VT-IT method? Across the network, you connect a voltage source VT, current flowing out of the plus terminal is what? IT, and then we have to find what? VT by IT. That's all. Okay. So what is this current? It is what? IT. Now at this point, IT is what? Entering, I is what? Leaving. If I ask you what is this current, you should say it is what? Like IT minus I. Yes or no? IT minus I. So because of this current, there will be some drop across, the 10 ohm resistor. Okay. So what is this drop? It will be 30 times I. In fact, we can write KVL around this loop, or else the better way to do it is what? By assuming ground. Okay. So just clear this off. See, in this circuit there is no ground, so let's assume this node to be ground. So once you assume this node to be ground, what is the voltage at this point? It is what? 20 I. What is this drop? It is what? I times 30, that is what? 30 I. Because this is what? Ground, we go from minus to plus. What is the voltage at this point? It is what? 30 I. Again, this entire thing is what? Ground. So what is the voltage at this point? It is what? VT. Okay. Now, what is this current? Or let me change the direction. What is this current? 30I minus 20I, which is 10I by 10. 10I by 10 is what? I. Okay. So now if you look at this particular point, IT is what? Entering. I and I both are leaving. So IT equal to what? 2I. Okay. And then this IT is equal to what? Vt, It is what? Current through 5 ohms, right? Vt minus 30I by 5. Vt minus 30I by 5. Because It is what? 2I. I is what? It by 2. Yes, on I is what? It by 2. Yes, I equal to what? It by 2. So 30I will be same as what? 15 It. So Vt minus 15 It by 5. That's all. 5 It plus 15 It. So Vt equal to what? 20 It. And RTH is what? Vt by It, which is 20 ohms. So what are the final values of VTH and RTH? No independent sources. Thevenin voltage is what? 0. Thevenin resistance, just now we found it to be what? 20 ohm. 20 ohms. So that means what? If you are standing here and if you look in this direction, this entire network will appear like a single resistance of value 20 ohms. Okay, that is the point. Okay, look at the next circuit. This time you are asked to find what? The Norton equivalent. Yes, across A and B. So this is A, this is what? B. So in other words, we have to replace this network with a single current source in series with, in parallel with a single resistance. Yes, so Norton equivalent means what? Current source in parallel with resistance. Okay. Again, if you notice, inside the box, are we having any independent sources? Resistor, this is what? Dependent source, but there are no independent sources. No independent sources. Directly we can say every current, including what? The short circuit current is what? 0. So no independent sources. So the value of ISC is what? 0. That means the value of the Norton current is also what? 0. So now the only thing we have to find is what? The Norton resistance. And remember, the Norton resistance is same as what? The Thevenin resistance. Okay, so finding Rn is same as what? Finding the value of RTH. Again, because of this dependent source, we cannot find R equivalent by using series parallel combination. You have to use what? The VT-IT method. Okay, so let us find RTH using what? The VT-IT method. Okay, so what is that VT-IT method? Outside the network, we have to connect a voltage source VT and then let this current be IT, and then we have to find what? VT by IT. So what is V1? It is what? VT. It is what? VT. Okay. So here I think we can do source transformation. On the right hand side we have what? 0.1. So what will happen to this 0.1 V1? It is same as what? 0.1 VT, because V1 is what? VT. Because 100 ohms is what? Directly across voltage source VT. Okay. Dependent current source in parallel with resistance can be transformed into a dependent voltage source in series with the same resistance. What is the value of the dependent source going to be? 0.1 VT into 200. 0.1 VT into 200 will be what? I think 20 VT. 20 VT in series with 200, and then the 200 will appear in series with 50, which is 250. Okay. So it will look something like this. So you'll have what? A 250 ohm resistor, and then in series with that you'll have what? A dependent voltage source of value 20 Vt. Okay, 20 Vt. I think this is good enough, right? Yes. So what will the total circuit be? So this is what Vt, and then we have what the 100 ohm resistor, across which the voltage drop is what Vt. I mean V1, but V1 is what like Vt. Okay. And across this we have what 250 ohm resistor in series with a dependent voltage source of value 20 Vt, and of course this current is what It. Okay. Now here there is no ground. I'll assume this to be ground. Yes. If I assume this to be ground, what is the voltage at this point? It is what Vt. What is the voltage at this point? It is what minus 20 Vt, because you are going from plus to minus, you have to subtract the drop. Okay. So what is this current? It is Vt minus minus 20 Vt, which is 21 Vt by 250. And then what is this current? It is Vt by 100. Now at this point, It is what entering, and these two currents are leaving. So It equal to what? Vt by 100 plus 21 Vt by 250. So what is the LCM? I think 500. So it is what 5 plus 21 times 2 is what 42. And this is what Vt. So what is Vt by It? Clearly it is what 500 by 47. It is what 500 by 47. So 500 by 47 is what 10.63 ohms. That is the Norton resistance. So what is the Norton equivalent? It is 0. I mean Norton equivalent current, it is what 0, or the Norton current is what 0, and the Norton resistance is what 10.63 ohms. Again, for someone standing here and looking in this direction, he will only find what a single resistance of value 10.63 ohms, nothing else. Okay. So this entire yellow color box will appear like a single resistance of value 10.63 ohms. Okay. Okay, look at this circuit. So there is some network. There are two cases. In the first case, you have to find what the Thevenin equivalent across A and B. So this is A, this is what B. So when I say find Thevenin equivalent across A and B, it is understood that you are going to connect the load like this across A and B, and the polarity of the load voltage will be what? Plus on A and minus on B, because it is said find Thevenin equivalent across A and B. So A will be plus, B will be minus. Okay. So this is what the polarity of the load voltage. Even the load current will flow from A to B. Okay. This is what the direction of the load current. Yes. So there is the circuit for the first case where you are trying to find equivalent, Thevenin equivalent across A and B. So finding Thevenin equivalent again means what? Finding VTH and RTH. Okay, finding VTH and RTH. Okay, see. So first we'll find what? RTH. So finding RTH. What is RTH? It is what? R equivalent. R equivalent across what? across RL. Yes or no? RTH means what? Equivalent resistance seen by the load. Now while finding the equivalent resistance, you can make all the other independent sources 0. Yes, within the network you can make the independent sources 0. That means what? This voltage source will become what? Short circuit. Yes or no? This voltage source will become short. This becomes open. Even this becomes what? Short. Okay. Now if you observe, this is what? A. Now because A is short, this is also what? A. This is also what? A. This is also A. This point is what? B. Okay. Because this point is what? Short to this point, this is also what? A. Now the point I am trying to make is what? This. RL connected between what? A and B. 2 ohm also connected between what? A and B. This 2 ohm also connected between what? A and B. Now we have 3 resistors connected between what? A and B. RL, this 2 ohm and also this 2 ohm. So can we say all are in parallel? So when you have 2 ohm and 2 ohm in parallel across RL, what is the equivalent resistance across RL? 2 ohm parallel 2 ohm, which is 1 ohm. So what is the Thevenin resistance? It is what? 1 ohm. Okay. Now let us find the Thevenin voltage. What is the Thevenin voltage? It is the open circuit voltage across the load. Okay. We just redraw the network. So again, I have drawn the same network. So this is what A, this is what B. So if you are finding what? VTH. So finding VTH means what? Finding VOC. So while finding VOC, you should remove the load. And when you remove the load, you will get what? An open circuit, and that open circuit voltage is what? This. So this polarity is same as what? The polarity of this VL. So what is this voltage drop? It is what? VOC. Okay. Now you have to do the analysis and find what? VOC. Okay, again this is what? Like point C. So what is this current? It is what? 0. Okay. So what is this current? It is what? VOC by 2. What is this current? It is what? 0. Now at this point, point 1 is entering, VOC by 2 is also what? Entering. So what will this current be? This current will be what? VOC by 2 plus 0.1. Yes or no? Writing KCL here will give you what? VOC by 2 plus 0.1. This will result in a drop across 2 ohms with this polarity. Okay. Now we can write KVL around this loop starting from this point. What is that KVL equation going to be? Minus 2 plus VOC plus the drop across this 2 ohm, which is current times 2 ohms. VOC by 2 into 2 is what? VOC. And then 0.1 into 2 is what? 0.2. And then plus 4 equal to what? 0. Yes, VOC plus VOC is what? 2 VOC. 4 minus 2 is what? 2. 2 plus 0.2 is what? 2.2. So we are going to get 2 VOC equal to what? Minus 2.2 volts. So VOC is what? Minus 1.1 volts. So that is what? The value of VTH. So what is the value of VTH? It is minus 1.1 volts. And of course we already found RTH to be what? 1 ohm. These are the values of VTH and RTH. Okay. So in the other case, you have to find what? The Thevenin equivalent across B and C. So in the other case, your load will be connected across what? B and C, and B will be what? Plus and C will be what? Minus. Even the load current is going to flow from B to C. So please follow a similar procedure and find the Thevenin equivalent for the B case. So I'll leave it as homework. Okay. So B case is what homework. Okay. Okay, look at the next circuit. So there's some circuit and the question is what to find Thevenin equivalent across A and B. That means this network should be replaced with a single voltage source in series with a single resistance. Okay. This time we cannot say that the Thevenin voltage is what 0 because there is what an independent source. If there is an independent source, if there are no independent sources, then VTH will be what 0 and all that. Okay. So here we have to find what VTH and RTH. There are many ways to do it. You can separately find VOC and ISC. Yes. I mean here you can, if you want, you can connect the load. This is what the load voltage, this is what the load current, and then you can find what VOC by removing the load, and then you can find ISC by shorting the load. Okay. From VOC and ISC you know how to find VTH and RTH. But I will do it using what the VT-IT method. Okay. So across A and B, I am going to connect a voltage source VT and let this current be IT. What is the standard relation between VT and IT? Yes, VT equal to what? AIT plus B. So we'll try to get a relation which looks like VT equal to what? AIT plus B, and then A becomes what? RTH and B is what? VTH. Okay. So it is quite simple. So what is this current? It is what? IT. Yes. So what is this drop? It is what? 2 IT. Yes, and it is what? 2 IT. And then what is this current? It is what? IT. What is this current? It is what? 5 amps. Now we can write KCL at this point. IT plus 5 equal to what? I. That is the KCL here. And then this drop will be what? 10I. And then we can write KVL around this loop starting from this point. So minus 10I minus 3I minus 2IT plus VT equal to what? 0. So VT equal to what? 2IT plus 13I. But then I is what? IT plus 5. So 2IT plus 13IT plus 13 times 5 is what? 65. So 2IT plus 13IT is what? 15IT. So finally VT equal to what? 15IT plus 65. Now you have to compare this with the standard form. VT equal to what? AIT plus B. So your RTH is nothing but A, which is what? 15 ohms, and VTH is nothing but B, which is 65 volts. Okay. So these are the values of VTH and RTH, 65 volts and 15 ohms. Okay. Is it not quite simple? Okay, look at the next circuit. So here also we need to find what? The Thevenin equivalent across A and B. Thevenin equivalent across A and B. So what is the actual network? This is what? Like the actual network. And within this network, there are 2 dependent sources but no independent sources. So directly we can say VTH equal to VOC equal to what? 0. So the only thing we have to find is what? RTH. And because of the presence of dependent sources, you cannot find RTH directly. You have to definitely go by the VT-IT method. You have to use what? the VT-IT method, okay. But before using the VT-IT method, let us try to simplify this by using a bit of source transformation, okay. If you look at this current source, it is in parallel with this resistance, which can be transformed into what? A dependent voltage source in series with the same resistance. What is the value of the dependent voltage source? 0.01 VAB into 200. I think it will be 2 VAB. 2 VAB in series with 200 ohms, and then the 200 ohms will be in series with 50 ohms. 200 series 50 is what? 250, okay. Even that 2 VAB dependent source will be in series with the other dependent source. So this will be plus minus like this. Plus is connected to what? Minus. So both the dependent sources can be combined into what? A single dependent voltage source. Okay, I hope you are getting what I am trying to say. Okay, so 2 VAB plus 0.01 VAB. So finally, this can be simplified into what? A single dependent source of value 2.01 VAB in series with a single resistance of value 250 ohms connected between what? The 2 points A and B, and then we will connect a voltage source across this network. Let this current be IT, okay. And by the way, this drop is what? VAB. Now what is VAB? Is it not same as VT? VAB is same as what? VT, okay. Now what is this current? It is what? IT. So what is this drop? It is what? 250 IT. Now we can write KVL around this loop starting from this point, okay. So if you write KVL around this loop, minus 2.01 VAB, but remember VAB is what? VT. So directly I'll write VT. So minus 2.01 VT minus 250 IT plus VT equal to what? 0. I think 1.01 VT equal to what? Minus 250 IT. So what is VT by IT? It is minus 250 by 1.01. So which is approximately, or let me find the value, 250 by 1.01, 247.5 minus 247.5. So what is VT by IT? Is it not RTH? Yes. So finally, VTH is what? 0, whereas RTH is what? Minus 247.5 ohms. So look at the RTH value. Is it not negative? Because RTH is not a physical resistance. It is only what? An equivalent resistance. So when you look into that network, what is the equivalent resistance? You will see that is the Thevenin resistance. Generally RTH is what? Positive, but if the network has dependent sources, then RTH can be negative as well, okay. So if you look into this network from outside, this entire yellow color box will appear like a negative resistance of value minus 247.5 ohms. I hope it is clear, okay. So what is the point? If a linear network does not have dependent sources, then RTH is always positive, okay. If a linear network If a linear network does not have dependent sources, then RTH is always positive, and if a linear network has at least one dependent source, if a linear network has at least one, then RTH can be either positive or negative, or even can be anything. Then RTH can be what? Anything. It can be negative as well, or it can be negative or positive. I hope you get the point. Okay, no dependent sources, RTH always positive. If there is at least one dependent source, then it is possible for RTH to become what? Negative. Okay. Okay, please look at the next circuit. Say some circuit, it contains what? One voltage source, second voltage source, third voltage source. It also has three resistors. Okay, three voltage sources and three resistors. And the question is what? To find the Norton equivalent across the 2 points A and B. So this is what A, this is what B. So you have to find the Norton equivalent. Norton equivalent means what? This entire network should be replaced with one single current source in parallel with one single resistance. Okay. Now if you observe, this voltage source is in series with 5 ohms between what? A and B. This 30 volt source, it is in series with 20 ohms also between A and B. And this 20 volt source, it is in series with 10 ohms also between what? A and B. Yes. So between A and B, we have three branches in parallel. Yes or no? Between A and B, we have three branches in parallel. Every branch contains what? A voltage source in series with resistance. Okay. So you have to redraw this. So let's say this is what? A, this is what? B. Okay. Sorry. So this is A, this is what? B. So let's say the first branch is what? 10 volts in series with 5 ohms. Okay. Be careful about the polarity while redrawing this network. For the 10 volt source, minus is connected towards what? A. 10 volts in series with 5 ohms. And then we have the 30 volt source. For the 30 volt source, plus is connected to what? A. And 30 volts is in series with 20 ohms. Okay. So this is what? 30 volts. This is what? 20 ohms. And then the 20 volt source is in series with 10 ohms. 20 volt source plus connected to what? A. That's all. This is how the original network can be redrawn. And now what? We have to transform this into a single current source in parallel with a single resistance. That can be easily done using what? Source transformation. So 10 volts in series with 5 ohms will become what? 2 amps in parallel with 5 ohms. And then 30 volts in series with 20 ohms will become what? 1.5 amps in the upward direction in parallel with 20 ohms. And 20 volts in series with 10 ohms will become 2 amps in parallel with 10 ohms. 2 amps will flow in the upward direction. That's all. So again, this is what A, this is what B, this is what 10 ohms. Now this 2 amps and this 2 amps both will get cancelled out. Yes or no? Because 2 amp and 2 amp are in opposite direction. Now the only current source that will remain is what? This. So finally we get what? A single current source of value 1.5, and then in parallel with this we'll have what? 5 parallel 20 parallel 10. So what is 5 parallel 20 parallel 10? There it will have some value, okay? 5 parallel 20 parallel 10, okay? So this is going to be what? Rn, okay? That's all. So this is A, this is what? B. So now what is the Norton current? It is 1.5 amps. And what is the Norton resistance? It is what? 5 ohm parallel 10 ohm parallel 20 ohms. So in this way we can find what? The Norton equivalent, okay? So this is the last problem for the session. Please look at this circuit. You have to find what? The Thevenin equivalent across the 5 ohm resistor. That means what? This 5 ohm resistor is like the load, and with respect to the load you have to replace the entire remaining network with the Thevenin equivalent. So what is VTH and what is RTH? This is the question, okay? So you can find the Thevenin equivalent in a number of ways. You can remove the load to find VOC, or you can replace the load with short circuit to find what? ISC. From VOC and ISC you can easily find RTH. Already VOC is nothing but VTH, okay? But I will do it using what? The VT-IT method, okay? See, 2 amps, 1 ohm, this is also what? 1 ohm, this is 2 ohm, this is Vx, this is 4 Vx, this is 4 volts. That's all. This is what? The original network. Now the 5 ohm is what? Like the load. Now if you are going to find Thevenin equivalent using that VT-IT method, you should replace load with a voltage source Vt. So in place of load I have to connect the voltage source Vt, and then let this current be It. So because there are independent sources within the network, yes or no? This is what? One independent source, this is another independent source. VTH or VOC will not be 0. So what is the relation between VT and IT going to be? VT equal to what? Some AIT plus B. You have to get that relation, okay? So you can do this in multiple ways. What is this current? It is what? 2 amps. What is this current? This current will flow like this. So this current is what? IT. Yes. And then what is this current? It is what? IT plus 2. Okay. What is resulting drop across this? IT plus 2 into 1. Okay. And then you can find Vx. See, we have to apply, we have to write KVL around this loop. So we have to write KVL around this loop. We have to write KVL around this loop. Let us start from this point. Before that, Before that, let me write the value of Vx as what? Vx is what? Drop across 2 ohms, through which the current is what? IT plus 2. So 2 IT plus 4. That is what? Vx. Now if you write KVL starting from this point, you would get minus 4 Vx minus Vx minus the drop across 1 ohm, which is minus IT minus 2, and then minus 4, and then plus Vt equal to what? 0. So the first two terms will add up as what? Minus 5 Vx, and then Vx is what? This. So I think this will be minus 5 times 2 IT is what? Minus 10 IT, and then minus 5 times 4 is what? Minus 20, minus IT, minus 2 minus 4, I'll write it as what? Minus 6, and then this is what? Vt equal to what? 0. Yes. And then finally we get minus 10 IT minus 1 second, minus 5 Vx, this is correct. So minus 10 minus 1 is what? Minus 11. So I am getting this Vt equal to what? 11 IT plus 26. Now if you compare this with Vt equal to what? A IT plus B, directly we will get the values of Vth and Rth. So Vth is what? 26 volts. Rth equal to what? 11 ohms. So these are the values of Vth and Rth. Okay. So this is everything about the Thevenin's theorem. So whenever you have a linear one-port network, and if you are interested in voltage and currents outside this linear one-port network, then you can always replace the linear one-port network with its Thevenin equivalent, okay, which contains Vth in series with Rth. And we have seen plenty of examples about finding the Thevenin equivalent of any given network. So I'll see you in the next session, okay. So today I'll take at least one more session, okay.